Hi, thanks for joining us on Space Nuts. My name is Andrew Dunkley, your host. It's so good to have your company again. Coming up this week, we are going to look at magnetic fields in the sun's corona. Apparently, they've been mapped. What does that mean? It means you could drive a car there. Earth will get a mini-moon and it will hang around for a couple of months before it realises what it's got into, and then it'll take off again. And a new study has challenged the Big Bang Theory. When I say a new study, it's a redo of an old study. We'll tell you all about it on this episode of Space Nuts.
15 seconds. Guidance is internal. 10, 9. Ignition sequence start.
Space Nuts.
5, 4, 3, 2.
1, 2, 3, 4, 5, 5, 4, 3, 2, 1.
Space Nuts.
Astronauts report it feels good.
And I'll start off with an apology. If you can hear sound leaking in from another room, that is sadly Coco Melon. We're babysitting the 2-year-old. And if I hear another Coco Melon song, I am going to shoot myself to the sun, and that'll be that. Anyway, all that stuff aside, we say hello again to Professor Fred Watson. Hello, Fred.
Hi, Andrew. Well, at least if you shoot yourself to the sun, we're going to give you a map today, so you'll be able to find your way back.
That will be handy. Although I think I know where it is.
Well, that's right. Yes, most of us know where it is.
Yeah, it's just a long walk. Mm. Yes. What's happening with you? Hopefully not Coco Melon.
Well, look, it's been a very pleasant weekend with celebrating Marnie's birthday, so we've had a party and a few things like that. Yes.
Wonderful.
All good. Thank you. All good.
Wonderful. Shall we get down to business? Magnetic fields in the sun's corona have been successfully mapped. What does this mean? Now, before you talk, the sun's corona is something we really only can see during an eclipse. Is that right?
Yes, normally speaking, that is correct. It's the outer part of the sun's atmosphere. So the bit we can see is called the photosphere, and then there's a bit above it called the chromosphere, which we don't see very clearly. But above that is the corona, and both the chromosphere and the corona are revealed when the moon covers the sun's disk in an eclipse. And the reason why it takes an event like that to show them up is that the corona is sort of on average less than a millionth of the brightness of the disk of the sun. And so, you're looking at something really faint in terms of, comparatively speaking, with the disk. And so in order to observe it, you need the disk to be effectively removed, which is what happens during a total eclipse of the sun. But there's also an instrument which is called a coronagraph, and the name gives it away immediately. It's to photograph the corona. And they were developed back in the day, probably in the early part of the 20th century. And what it is simply a disk that you put over the sun's image in the focal plane of the telescope. So you block it out, and then you can, under certain circumstances, see the corona around that artificial disk. It's like an artificial eclipse. The problem is that what causes the corona to be invisible most of the time is the scattering of light by the Earth's atmosphere. So that technique with a coronagraph works really well if you're in the vacuum of space. All you do is put your disk over the sun's disk, and sure enough, you can see the corona. On the surface of the Earth, it's a lot more difficult, unless you go to the top of a high mountain where the atmosphere is really clear and there is not that much scattering of the light, the sunlight, into the region where the corona is. So it needs a telescope on a high mountaintop to do this. And sure enough, these measurements have been made by exactly such a telescope. It's called the Daniel K. Inuya Solar Telescope. It has a mirror 4 meters in diameter, Andrew. I think it's the biggest solar telescope in the world. And it's one that's, I'm very fond of it for a number of reasons. I've visited the place where it is located, which is the summit of Haleakala, the mountain, sacred mountain, on the island of Maui, in the Hawaiian Islands. Haleakala is at 3,000 meters, 10,000 feet, thereabouts. And several visits I had during the 2010s, I think it was, when this telescope was being built. So I watched the structure growing larger. And then the last time I saw it, Andrew, I was standing in front of it with Marnie as we got married.
Way!
Because we got married in front of the Daniel K. Inuya Solar Telescope.
How wonderful.
On the summit of Haleakala. Yeah, it was. It was very, very special. We eloped. I've probably told you this story before, because half my family's in the UK and half our family's in the UK and half is in Australia. So rather than miff one or the other of those groups, we got married. With both of them, we got eloped. There was a lovely Hawaiian celebrant in Hawaiian traditional dress, and a photographer, and us, and that was it. And there were a few people visiting the mountain just as tourists, and they gave us a clap at the end of it, which was really
how lovely.
Nice.
Oh, wonderful. Yeah, what a great place to get married.
It was, yeah. And we actually, the plan was to revisit it on our first anniversary, but something called COVID-19 stopped that, so we didn't manage to do it.
That'll happen.
Anyway, that's not the story.
No, well, it's a good sideline, though.
Yeah, it's a good, nice intro. So it's nice to see. And actually, I should, a shout out to the Inuya telescope. It produced the most stunning sort of normal visible light images of the sun's photosphere, the surface, where you see these what we call granules. They're convection currents in the sun's disk, and you can see them. They're just a few 100 kilometers across. You see them at high resolution with this wonderful telescope, and they are quite extraordinary with something quite new that was discovered with this. I think we covered this back at the time. It was a few months ago. Bright patches between the granulations, the convection currents. These convection currents have usually got a dark edge to them, and so they're almost like pixels on a photograph, but with a dark edge around them. And occasionally there's a bright spot in those, which was a new discovery from the Inuya telescope. But what it's discovered this time is something quite different. And as we said at the beginning, it's observed the corona. It uses a coronagraph. And so it has used its very, very fine capabilities to analyze the magnetic field in the corona. The corona, we know, is highly magnetic. And you might remember seeing pictures of total eclipses, Andrew, where the corona has structure in it. It's got what we call striations, these basically linear features, which tell you, because they look exactly like the good old iron filings and magnetic on a bar magnet. Yeah, they are the sun's magnetic field on a large scale being revealed to the naked eye by the corona. But what the Inuya telescope has done is taken it a step further, because there is a way of using light to actually directly measure magnetic fields. And what you have to do is take the spectrum of the light, and there is something called the Zeeman effect, named after a Dutch scientist. The Zeeman effect, what it does is the spectrum lines, those sort of barcode features in a spectrum, they're split into a pair by magnetism. So magnetic fields split spectrum lines into two by the Zeeman effect. And that means that if you're clever enough, you can map out where a magnetic field lies on a distant object. It's how we know that stars have magnetic fields. It's also how we know that there are magnetic fields around sunspots, but those are observations that go back to the 1950s, probably. It's only now that we have the technology to look at the corona and apply the Zeeman effect in the spectra of the sun's corona and chart out the magnetic field. And it's still a fairly rough and ready map, I have to say, but it's there. You can see how the lines of magnetism in the sun's corona, how they actually mimic what you see from the sun's disk with these features that we call prominences, giant clouds of plasma, which themselves follow magnetic fields. So we now have this map, and really quite spectacular in terms of what it means that you can actually take the sun's corona, analyze it in much more detail, and essentially give us a sort of roadmap for solar physics for some time to come. In fact, there's a lovely quote from Dr. Carrie Black, who's the National Science Federation Program Detector for the National Solar Observatory. Carrie says, "The invisible yet phenomenally powerful forces captured in this map will propel solar physics through the next century and beyond."
Wow. Yeah. I think one of the other major factors in achieving this is what they'll be able to do with space weather forecasting.
Yes.
That's pretty exciting stuff because, one of the big concerns about the sun is what it can do to our electronics. If there's a big, broadside hit from the sun, it could wipe out electronics, and there have been records of this happening, well, for over a century now. But these days we are so reliant on electronics, and everything's got electronics built into it just about, including people.
Including people, that's right.
They to be able to predict and avoid these kinds of problems would be a big step forward, I think.
Indeed, that's absolutely right. And but yet there's more.
Aha.
And that is, and it's highlighted by a quote again. I'm going to read from this is, I think, a press release from the National Solar Observatory. It's been carried on Space Daily, one of the well-known space and astronomy websites. It's a quote from the director of the National Solar Observatory, Christoph Keller. And Christoph says, "Mapping the strength of the magnetic field in the corona is a fundamental scientific breakthrough, not just for solar research, but for astronomy in general. This is the beginning of a new era where we will understand how the magnetic fields of stars affect planets here in our own solar system and in the thousands of exoplanetary systems that we now know about." So it's painting a broader picture. It's not just about the sun or space weather. It's going to tell us about exoplanets as well and how they react to the magnetic activity of their stars.
Magnificent, yes. If you would like to read the story, it's at spacedaily.com. But if you want to read the whole report, and I know a few people really are into that, science.org has published the report on this particular study. This is Space Nuts, Andrew Dunkley with Professor Fred Watson. Now let's take a little break from the show to tell you about our sponsor, NordVPN. Now, not so long ago, I did a bit of a speed test, just ad hoc speed test. Didn't plan it, just went ahead and did it on the spot to prove that you do not lose very much speed using NordVPN on your desktop computer or your laptop for that matter. I thought I'd test it on my mobile device, which I haven't done in recent times. So I've got my phone here. I've got the speed test icon going. So I'll do a speed test without using NordVPN. So here we go. And it is connecting and doing what it does. Boom. Okay, there's it peaked at 135, but it's hanging around the 115, 116 mark. So I'm going to close that. Then I'm going to connect NordVPN to my phone. And we are ready to go via NordVPN this time. And I'll hit go and we'll see what happens. So this is going via Central Australia. And I'm still achieving speeds of about 70 to 80 megabits per second. I am losing a bit, but it's not a lot. That's still really good speeds on a mobile network. The upload speed is actually faster. My upload speed is pushing up towards 10 megabits per second. Now it's just hitting 11. So with NordVPN, I lose a bit on the download, but I gain almost double on the upload, which is extraordinary. Now, they've been our sponsor for quite some time. I use all their products. I've signed up. There's a special URL if you're interested in looking at NordVPN as a Space Nuts listener. To get the best discount off your NordVPN plan, go to nordvpn.com/spacenuts. Our link will also give you 4 extra months on the 2-year plan. There's no risk with Nord's 30-day money-back guarantee. And I'll add the link to the show notes. And they back their products, not just the high-speed VPN, but the malware protection, the tracker, ad blocker, cross-platform password manager. That's my favourite thing in the world. The data breach scanner and a terabyte of cloud storage. Depending on which plan you get, you can combine all those things. So nordvpn.com/spacenuts is where you go, and check out the deal today. You won't regret signing up with NordVPN. Now, back to the show.
Roger, you're loud and clear here also.
Space Nuts.
Now, Fred, from the mass of the sun to a mini moon, which Earth will capture and may, by the time this particular episode's been released, have captured it. This has been happening semi-regularly by my estimation. I think this is the 3rd time in the last 20-odd years that we've picked up a passenger.
That's correct, yes. And I guess the reason why, we see these events happening is just because our instruments are now so much more sensitive. We have a whole plethora of telescopes looking at the Earth's environment, and part of that is to, what you might call planetary defense. It's to prevent the possibility of something taking us by surprise and knocking out a few dinosaurs and things like that. Yeah. So we now know much more about the Earth's environment, and we do know, as you've said, that from time to time, an object that is in an orbit that's not that different from the Earth's orbit can be captured into its own orbit around the Earth briefly before gravitational forces actually disrupt it and send it off in another direction. And a paper that's come from a group of scientists sat in Madrid, in fact, in Spain, actually talks about a particular asteroid for which that is, in fact, I think it's probably happening as we speak, Andrew.
Right.
For a couple of months, we're going to have a mini moon, which rejoices in the name of 2024 PT5. It's an asteroid, a near-Earth asteroid, and it's basically, as it's come close to the Earth, it has fallen into an orbit around the Earth, and it'll orbit for about 2 months, and then it'll go somewhere else as its path is perturbed again. We do know that this object won't collide with Earth, but having it as a mini moon for a while is perhaps a nicer thought.
How big is this thing?
It's about 10 meters, so size of a coach or a bus.
Yes, yeah. What would a 10-meter rock do to Earth or the moon if it hit us?
It's one of those events which would be comparable probably with the Chelyabinsk asteroid back in 2013, when an object perhaps 15 meters across hit the Earth's atmosphere, exploded at a height of about 30 kilometers, became very, very bright as a result of that explosion, and sent people to their windows, whereupon 90 seconds later the shockwave came down and broke all the windows, which is why you had 1,000 injuries. Yeah. Excuse me. So it's that sort of level, a 10-meter rock. It is certainly not civilization threatening or anything like that, but it's big enough to do some damage if it hits in the wrong place. Yeah.
It's really an unfortunate coincidence, isn't it, that these sorts of rocks can hit our atmosphere, explode, we go, oh, what was that, run to the window, and then we get hit by the shockwave.
That's right.
Yeah, it is. It's not a good formula, really, but as long as it's not much bigger than that, it's reasonable. I suppose in history, these sorts of situations have probably been common where we've picked up a passenger for a little while.
That's correct. The point is that we didn't know about them before, because 10-meter objects were well below the the detectability by equipment that we had even 20, 30 years ago. We didn't have the equipment to do this. I didn't give you the one detail that it will only go around the Earth once, which will take a couple of months. It's a 53-day orbit, actually, which starts... so it hasn't happened yet as we're speaking. This might be in the past for people listening. Beginning of September 2024 is when it... I beg your pardon, the end of September 2024, when it actually is captured. And then sort of near the middle of November, it will be expelled again.
How do they calculate that? How do they know that it will be released?
It's because gravitational forces are so predictable, so well understood. What you do is you take into account the gravitational pull, not just of the Earth and the Moon, because they're the closest objects, but also the Sun and the planets as well. And you look at the way their individual gravitational pulls affect effectively the shape of space. This is where it becomes a relativity thing, because we know that gravity changes the shape of space and that objects run along straight lines in that distorted space. That's how orbital mechanics works. And so if you imagine space as a kind of like a bed sheet that's a bit bumpy, that's had a rough night spent in it by somebody, because of the interacting gravitational field of all the objects in the vicinity. That a valley through that lumpy mattress or whatever it is would be the line which an object would follow, and you can predict that pretty accurately with modern computing. And that's how they know what will happen with this object.
I find that extraordinary, given how much we don't know about gravity.
Well, we don't know what it is for a start. Yeah, all we know is how it behaves. Yeah. Yes, that's right. We do. We know how it behaves. But, and relativity actually describes that in a way that is so precise that we have not yet managed to find a flaw in it. It's good to at least 1 part in 10 to the 18. It's extraordinary how accurate relativity is. And of course, people are looking for flaws in relativity to see if we can spy some new physics that might explain some of the other things that we don't understand, like dark matter and dark energy.
So if Einstein never existed and didn't come up with his theory of relativity, would someone else have done it?
Probably, yes. But just to clarify there a little bit, I reckon that if we didn't know about relativity, Newtonian dynamics is probably good enough to predict that this object will be captured by the Earth. Relativity is usually comes to the fore when you're in really intense gravitational fields, but its effects are visible even in small gravitational fields like the field of the Earth. We know, for example, that the Earth's gravitational field does something called frame dragging, which is predicted by relativity. It pulls space around with it as it rotates.
Yeah.
But that's
about that, I think, too. Yeah,
we have. Yeah, that's an effect that's small compared with being able to calculate that a 10-meter object will be captured by the Earth's gravity for a month. That's a calculation that I'm pretty sure you could do it just on Newtonian mechanics.
How about that? All right. It's a great story. You probably pick it up in just about every news outlet around the world because they've all picked up on the mini-moon story. But if you want to read the truth, go to phys.org, phys.org. You're listening to Space Nuts with Andrew Dunkley and Professor Fred Watson.
Okay, we checked all 4 systems and keying with a go.
Space Nuts.
Last but not least, Fred, is a new study challenging the Big Bang Theory. Now, we've had listeners who've actually challenged the Big Bang Theory, and now we've got one official paper that is doing just that, and it's based on data that's probably over 100 years old. What's the story?
Well, yes, that's right. The idea is 100 years old. The data is more up to date than that. Okay. We have talked about challenges before because not very long ago we talked about a scientist, and I can't remember his name, but he's at the University of Toronto, and he was trying to account for how mature the young galaxies that the Keck telescope is picking up were, and thought we got the age of the universe wrong. I think his value was 27 billion years. I don't know whether that rings any bells, Andrew. We did talk
Yes,
about
it does. Yes.
and he had his theory had a mixture of the expanding universe, which is the conventional view, and something called tired light, which is an old idea. And indeed, this one that we're talking about now, which comes actually from an engineer at Kansas State University, Leo Shamir, that is, again, harking back to the tired light idea.
Okay.
So what is tired light? It's a theory that was proposed actually by an astronomer whose name is well known to us, Fritz Zwicky, because he was the guy who found dark matter. He, back in 1933, observed galaxies in a cluster. The cluster is the Coma Berenices cluster in the northern hemisphere. These galaxies were going too fast for their own gravity to hold onto them. If there was nothing there but the galaxies he could see, then the cluster would have evaporated billions of years ago. And so that led him to deduce that there was something that he called dark matter, actually, in 1933. I think his paper was published in 1935. But his theory of the universe, the redshifts that we measure, and the redshifts are basically the spectrum of galaxies being shifted towards the red. The conventional explanation of that, courtesy of Edwin Hubble and a lot of other people, is that we're seeing that because they are moving away faster. And the further away they are, the faster they're moving away, the greater their redshift. And that is exactly what you will get from an expanding universe. That's why it's the preeminent theory of the way the universe behaves. But the tired light theory said, well, maybe what we're seeing is not a redshift caused by expansion. It's a redshift caused by a loss of energy. Just the light is getting tired. It's been going for so long. And that the universe isn't expanding. That's the bottom line, which kind of flies in the face of our present knowledge. Now, Dr. Shamir has done some work in looking at the way galaxies are moving away from our own, apparently, their redshifts, in different places in the celestial sphere, if I can put it that way, around the two galactic poles. Those are the places at right angles to the plane of the Milky Way. So he's looked at the redshifts of galaxies at those poles, and essentially thinks he finds a difference that is something that is interpreted as being due to the tired light effect rather than the expansion of the universe. Okay. So now I'm not. I haven't really read the paper in detail, and so I'm not quite clear what differences have been found. It's a systematic difference in redshifts at the two poles, which suggest that there is an effect that is other than the expansion of the universe. I think what knocks this on the head as a theory for, a preeminent theory of cosmology, that the light is just getting tired, the universe isn't expanding, the light's getting tired. What knocks it on the head is that when you look at very high redshifts, what do you see? You see the Big Bang. You see the cosmic microwave background radiation. And that's what knocked the steady state theory of the universe on the head in the 1960s. And I think it will be very, very hard for a tired light theory to explain why we see the cosmic microwave redshift. Cosmic microwave radiation. So I think this is a really interesting piece of work. There is a paper in a journal called Particles. The paper is entitled "An Empirical Consistent Redshift Bias: A Possible Direct Observation of Zwicky's Tired Light Theory." It's very tentative, as you'd expect, but I suspect it will have probably a few papers being written to say, well, this is why tide light is not real.
Mm. Yeah, I think the peer reviews will be interesting.
Yeah, that's right. That's right.
I must confess, when I read the article, my first thought was, hang on a minute. Okay, if you're saying this, explain cosmic microwave background radiation, because that didn't get covered. But, I mean, if there wasn't a Big Bang, what else could possibly have done what has happened over the last 13.8 billion years? There's probably no other explanation, is there?
No, which is why we're forced to the Big Bang theory by Occam's razor. Occam's razor says you take the most straightforward explanation for something, and any other theory finds it really difficult to explain the cosmic microwave background radiation. That is there. It's the Big Bang. We can still see it.
Well, at least he tried to shed a little light on it. Boom, boom. Yes. If you'd like to read that story, as Fred mentioned, it's published in the journal Particles, or you can go to phys.org again and see what they have to say about it. You might have your own thoughts, and I'm sure it'll prompt a few questions. That brings us to the end. Don't forget to visit our website when you've got a few moments at spacenutspodcast.com or spacenuts.io. Plenty of things to see and do there. You can visit our shop. I haven't popped into the shop lately. What's in there? Oh, bubble-free stickers, unisex T-shirts. You'll both wear the same one at the same time if you like. I mean, it's up to you. There are mugs, there are caps, there are hats, there are hoodies, there are socks. I've got a pair of those, and plenty more. And there's books in there somewhere by a famous astronomer who shall remain nameless. Probably not, though. And whatever else you like, check out our shop at spacenutspodcast.com or spacenuts.io. We're all done. Fred, thank you very much.
Pleasure, Andrew. Good to talk. And
you too.
Lots more questions to come.
Yes, indeed. We'll catch up with you real soon. Professor Fred Watson, astronomer at large, and conspicuous by his absence is Hugh in the studio. And from me, Andrew Dunkley, thanks for your company. We'll see you real soon on another episode of Space Nuts. Bye-bye.
Space Nuts. You've been listening to the Space Nuts podcast.
Mission complete, Houston.
Available at Apple Podcasts, Spotify, iHeartRadio, or your favourite podcast player. You can also stream on demand at Bytes.com.
This has been another quality podcast production from Bytes.com.